All right, how's it going? Welcome back to another video here in the series on mechanics and relativity. We are still working through this section here on forces. It's kind of a long section, but it's a very important section to physics. Forces are kind of the cornerstone of physics, right? So it makes sense that we spend a lot of time going through it. And in the most recent video, we kind of took the first step in introducing a specific type of force rather than just saying we're going to define some general force in terms of some generalized potential energy, right? And in the last video, we introduced the gravitational force. We said that any object which has mass associated with it will be under the influence of the gravitational force. Any two particles that we saw in the last video, any two particles that have mass will have a mutual attraction to each other due to gravity. So we kind of introduced the gravitational force in a general sense. We talked about it just as how we did right now, and then we also kind of cleared up some common misconceptions that people initially have with the gravitational force. The first one was talking about how the gravitational potential energy is a 1 over r function. But when we sometimes talk about the gravitational potential energy on Earth, we think of it as mg times the height above the ground, where it's linear in the position rather than inversely proportional to the position. So we cleared up the misconception and showed that when we're talking about the gravitational potential energy of the form m times g times z, where z is your height above the ground or above some specified origin, that is simply an approximation of the universal gravitational potential when you are close to Earth and your height above the ground is much less than the radius of the Earth itself, right? So that was one misconception that we cleared up, and then another one was something that we've kind of been holding off for several videos, but we introduced it at the end, where we talked about finally the difference between the gravitational potential energy and the gravitational potential, right? And sort of towards the end of the video, and this is kind of what we have here on the board, there was this diagram where we talked about not just the relation between the gravitational potential energy, V of r, that common function we've been working with for a little while now, and the potential, phi of r. We related them through this, right? We said that the potential was the potential energy per unit mass. But we also used sort of this diagram to introduce sort of one final concept, which is the gravitational field, a vector field, g of r. And we saw some nice parallels kind of relating each of these four quantities together, right? We've seen a couple times now that the gravitational force and the potential energy are related by the negative gradient. And then the idea is that if you were to just divide each of these quantities, F and V, by the mass of your particle, maybe starting with F, if you divide F by the mass of its particle, you get the gravitational field. And if you divide V by the mass of the particle, you get the gravitational potential. So really, this expression is the same thing as this expression, but here we've just divided by a factor of the particle's mass on both sides of the equation, right? So there's kind of like this nice sort of web or diagram, if you will, connecting each of these four quantities, and that's kind of where we left off, just saying this is how four really important quantities associated with gravity are all related to each other. Now, in this video, what we're going to be doing is we're going to kind of take more of a closer look into how the gravitational force gets applied. What we've been doing here is talking about it in a general sense, but I want to go through kind of these specific examples of where we will see the gravitational force show up. And we'll go through 3 examples throughout the video, and I think it probably helps just to go through them one by one rather than talk about them all right now. So what I'm going to do is to start the video off, I'm going to erase sort of this diagram that we finished off with last time on the board. And I'm going to start by writing out an example problem on the first problem set in the course from Cambridge. If you click on David Tong's lecture notes, he has kind of towards the bottom of his page, he has a PDF for each of the 4 problem sets. I believe this is problem set 1, question 6. And we're just going to go through the first part of that question to introduce applying the gravitational force. Okay, so admittedly, there's a lot of text here on the board, and that's just because there's a lot of writing in the actual problem when you look at the problem set. I'll say that I'm not yet positive that I'm allowed to share full solutions to the problems that are publicly available. So what we're going to be doing here is not going through the full problem, but rather just to set up the problem. And in setting up the problem, I'm going to ask you guys, the viewers, a couple of questions, as well as the actual part of this question that's relevant. And that, I think, in itself will help us understand how to actually apply what we've been doing in the past couple videos. So here's the problem. It says, during a windy day on Earth, there is a bug, and this bug jumps from the ground while the wind blows with a velocity u. Now, usually when I'm going through these problems, what I like to do is I like to go sentence by sentence, and as soon as I'm done with a sentence, I like to extract as much information that I can out of that sentence. So that way, if it's a longer problem like this, you don't read the whole thing and get kind of confused as to what's going on, and then you have to go back again. So just with this first sentence alone, what I can do, and another common strategy in physics, is you can draw a picture of the physical scenario that you're trying to model. So it says here that we have a windy day on Earth, and a bug, is jumping from the ground while the wind is blowing with a velocity denoted by the vector quantity u. So if I just draw the ground here, I can draw my attempt at a bug. Admittedly, I'm not the best artist, but this is going to be my little bug right here. And this bug is jumping from the ground, something like this, and maybe it's jumping kind of in this direction, denoted by this arrow right here. And it says, while the bug jumps from the ground, the wind is blowing with a velocity u. Now, they don't specify what direction u is pointing in, but it's just some general vector quantity. So I can really draw this however I want, but I'll just put an arrow, maybe like this, to say that this arrow denotes the direction of the wind. And I guess the wind's going to be blowing from the right to the left in this picture. But because they didn't specify which way the wind blows, I'm just going to draw it in sort of an arbitrary direction. I could draw it however I want. Okay. Now, the next thing is it tells us that the gravitational acceleration is denoted by the vector quantity g, and the wind exerts a force equal to mk times the velocity of the wind relative to the insect. We'll stop right there because there's a lot to unpack in that sentence, right? We'll start with the first part where it just says the gravitational acceleration is g. So we can just denote that real quick. We know that, and maybe I'll actually pause this really quick. How would you draw out this gravitational acceleration vector? Okay, assuming we've paused the video or had time to think about it, we want to keep in mind here the scenario that we're working with. This line right here is supposed to represent the ground on Earth. And we can just ask ourselves, if this is the ground, which way does gravity naturally want to point? Well, it wants to point down, right? Things, when they are left in free fall, naturally want to fall down. So we're going to draw this gravitational acceleration vector not just in any arbitrary direction, but we know that it has to go in the downwards direction based off of what we know about gravity, right? So that's the direction of g. And then it says that the wind exerts a force equal to mk. And I want to just make sure we understand that for a second. Mk is a product of two variables, where m is the mass of the bug. Maybe we can just say that m is the bug's mass, however much mass it has, and k is just going to be some constant value to denote really the strength of this force right here. Now it says here that the wind exerts a force equal to mk times the velocity of the wind. Now keep in mind, the velocity of the wind is u, but it's not just mk times the velocity of the wind, it's the velocity of the wind relative to the insect. That relative part is going to take maybe just a little bit of understanding, but we'll get to that in a second. And then the final sentence, which is the actual question, all we've been doing is drawing pictures so far, is they want us to set up the equation of motion for this bug. Okay. Now what I'd recommend doing is take a minute to try to solve this yourself. Maybe pause the video, try to solve, or just to set up the equation of motion for this bug that's jumping. And then whether you get a solution or not, then we can unpause the video and we can either compare solutions or see where we got stuck. Okay. So when it tells us to set up the equation of motion for this system, the equation of motion, if we remember, is naturally going to be a differential equation. And the differential equation is typically denoted using Newton's second law by a second order differential equation, where we write out that mass times acceleration, right, as m times a, is equal to the sum of the forces acting on whatever object has associated mass m. So this is kind of our starting point, and this is usually our starting point when setting up the equation of motion. You write out Newton's second law here. This is Newton's second law. In this case, m denotes the mass of the bug. So what we're going to do here is we're going to, well, I'll just first rewrite the left-hand side real quick as, rather than m times a, where a is the bug's acceleration, I can just write that as the second derivative of the bug's position. That way, so we get the form that it's, or we get the idea that it's a differential equation, right? And then on the right-hand side here, this is the sum of the forces that are acting on the bug. So now we have to ask ourselves, okay, well, what forces are acting on the bug? And I realize there are a lot of arrows here, and I probably got this, probably didn't need to draw all these arrows. I did this to go just sentence by sentence here. But if we go back to the actual problem, we know that the gravitational acceleration is g, so gravity is acting on the bug. And that makes sense, right? The bug has mass, so gravity should be a factor. So for my first term, I'm going to write F sub grav. So this is the force due to gravity. But this is not the only force acting on the bug, right? We also said that there is a force, that the wind exerts a force on the bug. And the wind exerts a force equal to something, this thing that we still need to unpack. For now, I'm just going to write this as F sub wind. Okay. So this is my differential equation. I have two terms on the right-hand side, force due to gravity and due to the wind. And in order to find the equation of motion, all we need to do is to just find what are the specific forms of these two forces right here. Keep in mind, finding the equation of motion is not solving the differential equation. It's just setting up the differential equation in itself. So once we have the differential equation, that would be our answer. So let's start with the gravitational force. And let's ask, what is the gravitational force that's acting on this bug? Take a minute to pause and think about that. Okay, assuming we pause. I want to emphasize this because we saw in the previous video that we could either think of gravity as this constant force, m times g, or we can think of it as this inverse square law. And we saw how we were comparing kind of the two side-by-side terms. We were looking at the gravitational potential energy, right? But what do we put here? Do we put mg or do we put this inverse square law? And we want to keep in mind here that this is taking place on Earth, and the bug is very close to Earth. So this would fall under the approximation of the gravitational force when we have an object that is near the surface of the Earth. So because that is the scenario that we are working with, we are working in a scenario that is close to the surface of the Earth, we can approximate the gravitational force as just m times g. Now, whenever you have any problem, more or less, that exists on planet Earth, you have some object on Earth, which is a lot of things, right? Certainly everything that we encounter in everyday life. This would be the form of the gravitational force that you would use, as opposed to F equals gmm over r squared in the r hat direction. Okay. This is the approximation. It works well because we're near the surface of Earth. So that would be the first term. And then we need to find the force of the wind. Now, it tells us actually that the force of the wind is equal to something. It's equal to m times k. So I'm going to write that part of it. I'm going to write plus m times k, where m is the bug's mass and k is some constant denoting the strength of the force. And then it's multiplied by one other thing. It says it's multiplied by the velocity of the wind relative to the insect's velocity. Okay. Now it's at this point here where it's that relative to the insect that can be a little bit confusing. It could trip us up a little bit. So I want to just sort of unpack this and kind of come up with an easy way to interpret this sentence. The velocity of the wind relative to the insect. For now, let's just pretend that the relative part doesn't even appear anywhere. So it's just the wind exerts a force equal to mk times the velocity of the wind, and that's the end of the sentence. We already know that the velocity of the wind is denoted with the vector quantity u, so if there was no relative part, then the sentence is just literally telling us that the force is equal to mk times the velocity of the wind, which is u, right? Now, of course, the problem doesn't just neglect this final part, relative to the insect, right? We need to incorporate that. So what I want to do here is to say, let's almost consider sort of a slightly alternate scenario. Let's pretend this is the force right here. This is the actual force. What is another way of describing mk times u? And another way of describing mk times u, and I think we'll see what I mean here in a second, is if our actual force was mk times u, another way of writing this is if I were to put mk times u minus the zero vector, right? Because the u vector minus the zero vector is just u, and that gives us mk times u. So this would be essentially the same thing as just mk times u. Now, let's read out what this expression is, okay? And hang with me for a second. This will hopefully click in a little bit. The way that this would read, mk times u minus the zero vector, this is equal to mk times the velocity of the wind, u, relative to the origin. Okay? The zero vector is the origin of whatever problem you have. So this quantity right here, mk times u, is equal to mk times the u vector relative to the origin. So by framing it this way, u minus the zero vector is just u, which would be the u vector relative to the origin. Now what we're doing is we're rewriting this, or we're writing this in such a way that we're relating it to the word relative. So if this is mk times u relative to the origin, now let's just see, okay, well, what is the force relative to in our actual problem? In our actual problem, it's equal to mk times the velocity of the wind relative to not the origin, but to the insect. Okay? So rather than writing the zero vector, which would be the origin, what we would need to do is we would have to write out the velocity of the insect. Now, what is the velocity of the insect? We look at this diagram here and we don't see any velocity specific. We drew an arrow right here to physically show where the bug is traveling, but there's no notation to describe the insect's velocity. Keep in mind, though, that this is inherently a differential equation. So we're taking time derivatives of this x vector right here. So the velocity of the insect would just be the first time derivative of this position vector, x dot. So what I would put right here is x dot, like this. All right? And this is how we can read out the this force right here. It's mk times the velocity of the wind relative to the velocity of the insect. Right? So I realize it's kind of like an extended way of doing that, but hopefully by relating this as the velocity of the origin, the zero vector, we can just replace the origin with whatever the insect's velocity is. And then hopefully that makes sense. That's how I like to think of that whenever I read relative to something. So this is the equation that we have right here, mx double dot. And I guess the final thing that you could do is we see that every factor, or every term in this equation has a factor of n, the bug's mass. So that would cancel out. And the differential equation that we would be left over with would be this one right here. Of x double dot is equal to this constant vector g plus k times u minus x dot, the velocity of the bug. Right? So hopefully that makes sense. Now what I want to do before going on is to ask one sort of specific question, which is to say, what would happen if this scenario here was not taking place on planet Earth, but it was taking place on another planet, say Mars, for example? How would this differential equation change, if it would change at all? So maybe take a minute. I realize it's not on the board, but take a minute to think about that. And when you're ready to discuss it, then unpause the video. Okay, assuming that we've thought about it. If we were to talk about this taking place on another planet, there are two sort of main things that might potentially change. The first thing, and when I say two things that might change, the two possible things that could change are these two forces right here. This left-hand side is never going to change. This is just the left-hand side of Newton's second law, right? No matter what system you have on any planet, or not on a planet at all, you're going to have ma is equal to the sum of the two forces. So if we were on a different planet, let's maybe start with, I actually want to start with the wind force, for example. One thing that could possibly change is that the other planet that we're on, that's not Earth, may not have an atmosphere. And if it doesn't have an atmosphere, then there would be no force due to wind, because wind is inherently dependent on an atmosphere. Now, this is not to say that other planets do not have atmospheres. There are plenty of examples of planets which do have atmospheres. But this term may or may not depend, or it may or may not show up whether or not the planet itself has an atmosphere. Okay. So that would be the first thing that could change. I should also mention too that maybe the atmosphere has different physics associated. So even if it does have an atmosphere, maybe the form of the wind force may not take that specific form right there. But anyways, that's kind of the first thing that could possibly change if this were taking place on another planet. What about this term right here, the gravitational force, which is really what I want to focus on for this video. Now, keep in mind that when we came up with two expressions for the gravitational force, we came up with this constant mg that we used in this problem right here. And then we also came up with gmm over r squared, r hat. This was the general version of the gravitational force. This was the simplified form that we could use if we were working close to the surface of Earth. Well, now we're not working close to the surface of Earth. We're working close to the surface of another planet. So does this expression here still, is it still a valid expression to write down? Or do we need to all of a sudden write this expression right here? And the answer is, well, this expression is never going to be wrong. This is sort of the universal expression. But if you were to go through the simplification process that we did in the last video, you would see that you could still perform you could still make the same assumptions to go from here to this simplified expression, even if you were on another planet. And let's just remind ourselves why. Because when we went from this general case to this sort of specialized case right here, this relied on the fact that your height above the ground, which we can denote z, divided by the radius of the planet, which we can denote uppercase R, is much less than 1. And regardless of what planet you're on, if you have a bug that's just sort of jumping just a little bit off the ground, this ratio is still going to be significantly less than 1, and therefore this form of the gravitational force would still apply. So for the first part of this, how would this expression change right here? In its functional form, no. The force due to gravity, even on another planet, for this bug right here, would still have the form m times g. Now, what would change is the magnitude of g itself. Let's remind ourselves about how this quantity little g was computed in the last video. Or we talked about this excuse me, in the last video. We said that we could relate little g, we could compute little g by this product of quantities. We could compute it by big G times big N over R squared. And on planet Earth, this value is approximately 9.8 meters per second squared. Little g denotes how fast objects want to accelerate if they are in free fall. How fast does this thing want to accelerate towards the ground? Now, if we remind ourselves what each of these quantities are, in our expression for little g is equal to big G. Big G is the universal gravitational constant. This value will never change. So it's 6.67 times 10 to the minus 11 in standard units. So this number will be the same regardless of what planet you're on. However, these two quantities, the mass of your planet and the radius of your planet, those are going to vary from planet to planet. The mass of another planet is going to be different than the mass of Earth, and same thing with the planet's radius. So what would change if we were on a different planet is that we would still be able to write the gravitational force on this insect as m times g, but on another planet, g, and let me just specify this, because we're writing g with a vector sign here and just g without a vector sign here. This quantity right here is the magnitude of this vector, okay? So what would change when going from a different planet is that this quantity right here would have a different magnitude associated with it. You can still write it as a general vector g, but if you were to actually calculate its numerical value, that value would change from planet to planet. Okay. So I realize there's kind of a lot going on here, but hopefully that makes sense. I want us to really make sure we understand from the previous video exactly when do we apply one form of the gravitational force versus the other, and when do certain assumptions, when are they upheld, when do they fall apart, and what quantities change, because it might not be obvious when just working with variables by themselves, right? We don't always see the numerics or the numerical values of these things changing, right? So hopefully that makes sense. Now, next thing that I'm going to do, we're going to erase the board, and we're going to talk about a concept that shows up when talking about the gravitational force called a particle's escape velocity. So I'm going to erase the board, and then we're going to go through that next. Okay, so to introduce the idea of escape velocity, I'm going to start by drawing a picture, kind of like what we've done in the last whiteboard. So I'm going to start by just drawing somebody who is jumping in the air. All right. So we have our ground right here, and our human is jumping up in the air, and he's smiling, or she smiling. And they're happy for whatever reason. Maybe they're a kid and they're playing hopscotch, or they're an adult, they just got a promotion or something like that. But typically, I associate jumping with sort of this happy or positive type of event, right? On the other hand, though, you could take jumping and look at it in a much more cynical context, where you could think of planet Earth as having this gravitational pull which traps all humans to Earth's surface, and maybe we have some human right here that is no longer happy. Now the human is sad because the poor human is just trying to be freed from Earth's gravitational pull, and they're trying to jump to get away from to get away from Earth. But Earth says that even if you can get away from its gravitational pull temporarily, seemingly, you can get away from the Earth's surface, naturally its gravitational pull wants to drag you back down to the surface of Earth. And what we're going to look at here is, it's kind of a weird scenario because it's not the most physical thing. Humans by themselves can't actually do this. But we're going to ask, how fast would this human need to jump if it were to actually escape Earth's surface? Okay. And the velocity that's needed to escape Earth's gravitational pull is known as the escape velocity. Okay. So that's kind of where the term comes from. Now, to understand how to derive this, I want to start by just by writing out this human's total energy. And the total energy of the human gets split into a sum of two terms. It's kinetic plus potential energy. For the human's kinetic energy, that's always just going to be 1/2 mv squared. And then for the potential energy, the human is close to the surface of the Earth, so we might think that we would use the form of the gravitational potential energy, mgz. But we're actually going to use the universal gravitational potential energy. We're going to use minus gmm over r. We can always use the universal version. This expression right here works no matter what instance or no matter what your physical system is, whereas the expression I wrote up here only works if we're close to the surface of the Earth. But we'll see, we'll eventually get to why we're using this expression as opposed to that mgz expression that I just erased. All right. So this is the human's total energy, and what we can do with this expression here is we can go through a technique that we talked about in previous videos, where we look at the potential energy curve of this human. So let's draw that out over here. So what I'm going to do is draw out these two axes like this, where my horizontal axis is going to be this coordinate r right here. My vertical axis is going to be the gravitational potential energy v of r, which is minus gmm over r, right? Just to make sure that we understand what all the symbols represent, g is the universal gravitational constant. That's 6.67 times 10 to the minus 11 number. M is the mass of Earth. Little m is the mass of our human. Let's maybe give him or her a mass, little m. And then r is the distance between their center of masses. If I were to draw this picture in a more zoomed out context, I would have Earth right here, and we would have maybe our sad human right here. And this radial coordinate right here is the distance between Earth's center of mass and the human center of mass, which is approximately the radius of the Earth. Okay. Well, at least for this human, it's approximately the radius of the Earth. This coordinate, the radial coordinate, is just the distance between the centers of mass, the center of masses for both of the two objects in question, right? So what we can do now is let's first just sketch out what does this curve look like. And to do that, there are two things that we need to keep in mind. The first is that the potential energy is inversely proportional to the radial distance. So when r is small, the potential energy is going to be rather large. And as r gets larger, this fraction tends to 0, and then the potential gets progressively smaller. So it's going to be an inversely proportional relationship between v and r. And then there's also this minus sign. The minus sign is not there by accident. By default, we have kinetic plus potential energy. So the potential energy includes this minus sign right here. And the negative sign just comes from the fact that the gravitational force is an attractive force. It wants to bring things together. So the distance between them progressively decreases. So because gravity is an attractive force, that's why we have this minus sign. So with that in mind, we can roughly sketch out the form of our potential energy curve, even without knowing a lot of the specifics and plotting specific values. It'll look something roughly like this. Okay. So this is the curve for our potential energy, and unlike previous generalized potential energy curves that have a lot of local mins and local maxes, this is kind of just one decaying but still increasing curve, right? Now, what I want to do here is I want to not just draw out this curve, but I want to relate our human to the actual curve itself. Okay. And to do this, I think it'll be easy to start not with the human jumping, but when the human is just standing on the ground. Right? So maybe he tried to jump, or they tried to jump, but now they've gone back to the ground. They have failed to escape Earth's surface, and now they're here. Okay. At this point, when the human is on the ground, the distance between the human and the center of the Earth is quite literally the Earth's radius, uppercase R, right? So maybe at this point, this tick mark right here, maybe this will denote the Earth's radius, and we can kind of go down like this, and then we can draw the corresponding vertical point associated with it. At this point, V of R is going to be minus GMM, not over little r, but the specified value of R, the radius of the Earth. Okay? And what we can do is kind of like what we've done with previous potential energy curves, where we can imagine this potential energy curve kind of like a terrain. And if we were to place a ball on this terrain and kind of just let it be stationary, that is more or less equivalent to having just a human that is stationary on the surface of the Earth. Okay? So we're going to draw a little particle, a little ball, like this. This particle right here is supposed to correspond to this human. So these are two different versions of looking at these are two different ways of looking at the same physical scenario. All right. So hopefully that makes sense. Now, naturally, we would say, okay, the ball wants to kind of roll towards the bottom of this hill, right? The bottom of this hill goes towards decreasing values of R. That would be like if the human was kind of falling towards the center of the Earth. And that's what would happen if Earth was a point particle, right? But because Earth is not a point particle, it's more complicated than that. The Earth's surface, meaning the ground, kind of gets in the way of us falling towards the center of the Earth. So this picture is a little bit idealistic. It works under the assumption that Earth is a point particle. That's why it seems like the ball wants to fall off over here, but that's why it's going to just stay stationary. Because the actual potential energy for Earth, meaning the actual terrain of the Earth, is more complicated than just this right here. Okay. So even though this is slightly idealized in the sense that our particle, our person, is going to start on this part of the hill, and it's just going to stay there, we can still use this curve to understand the escape velocity. The question is, how do we do that, right? Now, in order to we can conceptually sort of understand the escape velocity in this picture, right? That would be like somebody jumping so fast that they are able to escape Earth's gravitational pull and traverse off into space, right? What does the escape velocity look like on this curve? Now, I know we said that the particle is standing still because we are standing still on the surface of the Earth, but just for imagine, let's pretend that the Earth is in fact a point particle and we're looking at this sort of abstract graph right here. This would be the curve for the gravitational potential energy, and if we were to place a ball at any point, seemingly any point on this curve, we ask ourselves, what does the ball want to do? Well, the ball wants to roll down over here towards decreasing values of R. Our 2 point particles want to come together. So what it would mean to escape the gravitational pull of the Earth is that we need to increase this particle's energy such to a point that it can more or less get over the local max of this hill right here. Then we ask ourselves, well, what's the local maximum? Well, we see that this curve is progressively increasing, and we ask ourselves, where does this curve want to tend to? Where is the highest point on this curve? The highest point is naturally going to be towards larger and larger values of r. As we get to larger values of r becomes very big. This fraction gets smaller and smaller. Or in other words, it gets increasing, or it gets progressively less negative. But in the limit as r goes to infinity, v of r is just going to go to 0, right? So it's almost like the local max is at 0. And if we could get our energy, this particle is going to have some energy right now, where it's located on the curve, right? If we could go from here and increase its energy so it goes above the local max, then we have gotten over kind of the hump associated with Earth's gravitational pull, and that amount of energy is what's needed to escape Earth's the tug of Earth's gravity. Okay. Now, to kind of get a little bit more quantitative, that's the intuitive idea with what we're trying to do here. We want to increase our particle's energy such that it gets over the local max, or it gets above v of r equals 0, which is this horizontal line, right? Let's first ask, all right, well, it clearly, if it's standing still right here, it doesn't have enough, it doesn't have energy to get right here, but what energy does it have? Well, if it's standing still, the particle's standing still, we're standing at rest on the surface of the Earth, we have, our velocity is 0 if we're just staying still, right? So that means all of our energy gets put into the potential energy term since this goes to 0. So what we could do is we drew out a curve of the potential energy, but if this particle is at rest, kind of like how we're at rest on the Earth's ground, then this horizontal line is not just the particle's potential energy, but it's its total energy. Or not E equals 0, excuse me. It's just its total energy, E. Now, I'm not just going to write E to be this particle's total energy. I'm going to write E sub I, the initial energy. Now, the initial energy is going to correspond to the energy of our human before the human decides to jump. But what we're going to see is when the human decides to jump, it's going to have a final energy, and by jumping, we are in fact increasing the human's energy. Now you might be saying, well, I thought energy was conserved, right? So isn't EI always equal to EF? Isn't the energy before always equal to the energy after? Isn't that what we learned? And the answer is, well, yes, energy is conserved. But what's really going on is that the way that we see how energy transforms when a human jumps does not always just get captured in this curve right here. This curve only looks at the gravitational potential energy. When a human jumps, it's converting the energy that's stored in its body, and it's converting it into kinetic energy that's allowing it to increase. So technically, energy is being sucked out of the human's body in some way, shape, or form, and it's being converted into kinetic energy, allowing the human to make that jump. All right. So in that sense, energy is conserved. But what it's going to look like is that when we jump, we are going to experience an increase in our energy. We're going to not only change this term right here, but this term is now going to change as well. When we jump, we're now going to have a velocity, so this term becomes non-zero. So with all of that in mind, we're saying that this is our starting energy. We want our final energy to be such that we have enough energy to get over the local max, which is at, we said, V of r equals 0, right? Now, if we had a final energy up here, maybe if this is E of f, this is enough to get over the V equals 0 barrier. If the line was right here, or if it was at any positive value, that's enough to get over the V equals 0 barrier. What we're going to ask ourselves is, what is the minimum amount of energy needed to get over that R equals 0 barrier? And that's essentially the value where we just reach the barrier, and we have some infinitesimal amount of kinetic energy after the fact. So the smallest amount of energy such that we can essentially reach this local max of V of r equals 0. That's going to be the minimum amount of energy needed to escape Earth's gravitational pull. So let's see how much energy do we need to go from our starting energy, E sub I, this line, up to the local max, which is this line right here. Maybe we'll put the local max at E sub F. Well, the amount of energy we need, we can write sort of by delta E. That is the total energy after minus the starting energy, like this. And if the final energy is at the 0 line, our final energy is just going to be 0, minus the initial energy before the humans started to jump. And we said that before the humans started to jump, when they were on the ground, all of their energy was potential energy. So their initial energy was this expression right here. So I'm going to have 0 minus negative G mm over r. Obviously, you just subtract these two, and that's just G mm over r. This is the amount of energy that would need to go into jumping in order to get to that local max at V equals 0. Okay. So let's now just say, okay, that's this right here. This is the change in energy needed to go from here up to here. That needs to be the energy that goes into the human's jump. The human's jump is quantified by its kinetic energy. So what we can do then is we can say the amount of energy that a human needs to jump, given by 1/2 mv squared, the amount of energy stored that goes into the human jumping needs to have this total energy such that it gets to the local max, right? So we set this term equal to this term right here, to G mm over r. And then it's at this point where we're just solving for V. What is the velocity needed to make the jump from here up to the local max? And just by solving this, we see that the little m's cancel out, meaning that the mass of the human actually doesn't matter. The escape velocity is the same for you as it is for me, for you as it is for me, as it is for a human with any mass or any weight. And then we just isolate for V here, and that just multiplies 2 to the other side and take the square root, right? So we end up getting that V escape. I'm going to write V sub ESE. The amount of velocity needed to escape Earth's gravitational pull is square root of 2gm over r, where g is the universal gravitational constant, m is Earth's mass, and r is the radius of the Earth. All right. I want to say it's on the order of, tens of thousands of miles per hour, I believe. It's something that, actually don't quote me on that, but it's something that is simply unobtainable by a human alone. But you could plug in the gravitational constant, the mass of the Earth, the radius of the Earth, and you could plug that in, and you could get an expression for the escape velocity. And that's how fast anybody would need to jump on Earth in order to escape the gravitational pull. Right. So hopefully that makes sense. It's kind of this interesting idea that can be solved for using relatively introductory physics. Now, to finish off the video, we're going to look at one more example of where gravity sort of shows up, and it has to do with this interesting and sort of fun little detail regarding the notion of a particle's mass. I'm gonna erase the board, write out 2 different definitions of mass, and we're going to discuss that to finish up the video. All right, so to finish out the video, I was initially going to talk about the difference between inertial mass and gravitational mass, but I just realized there was something I said I was going to cover in the previous whiteboard, and then I forgot to do it. So let me do that really quick. If you remember from the previous whiteboard, we said that the total energy of the human on Earth was the kinetic energy, 1/2 mv squared, plus the gravitational potential energy, gmm over r, right? And I initially said that there was a reason why we use this form of the gravitational potential energy as opposed to this sort of simplified form, plus mgz. And I want to make sure we understand why we use this form in that previous whiteboard as opposed to this form right here. Because after all, the example was just a human jumping on the surface of the Earth. It seems like that's somebody that is near the surface of the Earth, and that this simplification of this more general expression should apply. It seems like we should be able to just assume that this is the gravitational potential energy. So why didn't we? Well, it turns out, right, that this is the general form for the potential energy. This is the simplified form. And this form specifically works under the assumption that a certain ratio is upheld. The ratio is that if we were to take z over r, where z is your height above the ground and r is the radius of the Earth, if this ratio is much less than 1, that is quite literally the condition that allows us to go from the general form to this simplified form right here. And in most cases, when somebody's just jumping, your height above the ground is much less than the radius of the Earth. But in the case where you're talking about this extreme idea of an escape velocity, where you are jumping so fast, or you have such a fast velocity from the Earth's surface that you can escape its gravitational pull, now we're talking about getting to heights above the ground that are very large. And what happens is that when you're talking about the escape velocity, this ratio here of z over r is no longer significantly less than 1. So because this condition breaks down when talking about escape velocities in particular, that's why we had to use the generalized form for the gravitational potential energy as opposed to the simplified one, right? And again, we could always use this one too, right? This one always works. It's just that this one's kind of nice to work with in certain scenarios. But that's the reason why we did it. I want to make sure that that's clear. Now, to finish out the video, this is kind of a fun little just whiteboard talking about the difference between inertial and gravitational masses. First thing I want to do is just describe the difference between these two concepts, and then just roughly let us know where is physics currently at with the relation between inertial and gravitational masses. So when we have discussed a particle's mass up until this point, we would say that this is a particle right here, and it can have a numerical value attached to it that corresponds to its mass, right? And then any object that has mass is under the influence of or can be influenced by the gravitational force. It feels the effects of gravity. Now, it turns out that there are two main ways that you can look at, or you can think about the mass of a particle. And I want to make sure that we understand the distinction between the two, because they're actually quite different. Let's actually just start with the gravitational mass. In order to think about the gravitational mass, I'm going to write out the gravitational force between two particles that have masses. This is a particle of mass little m, this is a particle of mass big M, and because they both have masses, the gravitational force between them that we saw was gmm over r squared, right? And I think there's a minus sign, right, between the two. So because both of these particles have mass, they experience an attractive force due to gravity. And what we see here is that this left-hand side, this is the gravitational force, and this tells us how the gravitational force is constructed. What does the gravitational force depend on? What I'm now going to do is, rather than writing this little m as just m, I'm going to write this as m sub g, as the gravitational mass. What we're doing here is, by thinking of this mass right here, I'll also write a g subscript here, by thinking of this as the gravitational mass, we can think of the mass of this particle as a parameter that when the gravitational mass increases, so does the corresponding gravitational force between the two particles. And we can see this mathematically. As m sub g gets bigger, then F gets bigger, right? So it is something that tells us how strong the gravitational force is going to be between these two objects right here. It is a measure of the strength of this gravitational force between them. Okay. So this might sound obvious, and in some senses it is, but hopefully that makes sense. When specifically talking about the gravitational force, and let me even write grav to say that this is specifically the gravitational force, then the gravitational mass can be a parameter that describes the strength of the gravitational force between the two particles. Okay. Now, moving on to the idea of an inertial mass. We haven't gone through the concept of inertia, I don't think, yet at this point. We will definitely do it more later in the video series. But in general, the idea of an object having an inertia talks about an object's resistance to acceleration. Okay. And to see this, I think it's best to just write out Newton's second law in simple form. In simple form, Newton's second law just says F equals ma, right? Where F is the force on a particle of mass m, and it experiences an acceleration, a. If we were to isolate for the acceleration, we would get that a is equal to F over m. Notice this is for Newton's second law, and this is for a general force, F. This could apply to any force that you have. It does not need to specifically be the gravitational force. All right. That's kind of the first difference between the two. Gravitational mass specifically refers to a quantity related to the gravitational force. With the inertial mass, we have just an expression for a general force. And the main thing to notice here is that m is in the denominator of this fraction. What that tells us is that as m gets bigger, the acceleration gets smaller, right? The more massive something is, the harder it is to accelerate it. It's easy to push this pen. It's a lot harder, or it's easy to, push the pen from rest. It's a lot harder to push a truck from rest, because a truck has more mass, right? So the inertial mass can be thought of as a parameter that describes the resistance to acceleration, right? And the resistance to acceleration could be for any force, right? A force produces an acceleration. Any force produces an acceleration, but thinking of mass as an inertial mass describes its resistance to that acceleration. Okay. So there are very different ways of thinking about mass. One describes the strength of the gravitational force. One describes the resistance to the acceleration from any force. This one seems to want to slow things down, make acceleration smaller, where this seems to want to increase the strength of a force. So it seems like they're kind of different in how we conceptually think about them, right? But it turns out that they're not, up until this point, they are not actually different things. It turns out that all experiments up until this point have shown that the inertial mass m sub I is equal to the gravitational mass m sub g. And basically what this says is that even though these two ways of thinking about masses are very different from each other, for all intents and purposes, whether we think about mass as this mass right here or we think about mass as this mass, they're all one of the same thing. Meaning we don't need to worry about specifying an inertial mass or a gravitational mass through any problems in the video series. Now, this is not necessarily trivial, because thinking about mass in these two different contexts, it can be. I certainly think, at least, it's not trivial that whether we think about mass this way or think about mass this way, when we measure the mass of a particle, it seems that their inertial mass and gravitational mass are always the same thing. And people have tried to come up with differences between these two. And if I remember correctly, I think current estimates are showing that if you were to measure the mass of an object in two different ways, one way through Newton's second law, and another way through just the universal gravitational force law, that you're going to get the same thing for that particle's mass out, and it's accurate, I think, out to about 13 or 14 decimal places is where we're currently at. So if a particle's mass was like 3.627 ... kilograms, if you were to measure that particle's mass through this technique and through this technique, you would get the same number out to about 14 decimal places so far. And the precision is honestly incredible with how accurate they've been able to show that these two are really the same thing. The natural question is like, well, yeah, of course they should. Some people might think, of course they should be the same thing. Mass is mass, right? It's a fundamental property of a particle. But if we were able to show that there's a discrepancy between the inertial mass and gravitational mass, even if it's really tiny, meaning that you would have to specify what type of mass you're talking about when referring to a particle's mass, that has some interesting consequences in what would be future courses. I'll first say that this idea of the inertial and gravitational mass is kind of one of these results that is part of Einstein's equivalence principle. That idea would fundamentally break down, and there would be problems in his theory of relativity if that were to occur, if these were to found out to be different. And also that just leads to the possibility of new physics, right? A lot of just physics in general lies on the fact that the inertial and gravitational mass are the same. So there would be new things to discover if we found out that they were different. But main idea is that for all intents and purposes, when we say a particle's mass, doesn't matter how you think of it, you can just refer to it as its mass. Okay. So yeah, that's going to be it for this video. Thanks so much for watching, and in the next video we're going to move on to a different force, the electromagnetic force. So see you then.